Okay, we're going to have a look at a line that passes through the point with position vector 3, negative 4, or 3i, take 4j, and is parallel to this vector 2i plus 5j. And we're going to find the vector equation of the line, the parametric equation of the line, and the Cartesian equation of the line. So first of all, the vector equation of the line, which is straightforward. We can see that the line, this red line here, passes through this point with the position vector 3i take 4j, and it's parallel to this vector 2i plus 5j. So quite simply, our vector equation of the line is the position vector of any point on the line is given by this position vector of this point that the line passes through. So 3, negative 4. And then it's going to be plus lambda, some scalar multiple of the vector that the line is parallel to, which is 2i plus 5j. So there's our vector equation of the line, and that describes any point on that line for different values of this scalar lambda. The parametric equations of the line, to do that, what we first of all do with the vector equation of the line is express that in component form, or I component, j component form. So if we do that, we could say that the position vector of any point on the line is given by the I components, which would be 3 plus 2 lambda, and the j component, which would be negative 4 plus 5 lambda. So there's our I component, 3 plus 2 lambda, and j component, negative 4 plus 5 lambda. So from there we can separate out our parametric equations. We can say, well, the x value is actually equal to this I component. So the parametric equations of the line x is equal to 3 plus 2 lambda, and y is equal to negative 4 plus 5 lambda. So these are the parametric equations. They introduce x and y in terms of this other parameter lambda. So hence the parametric equations. We've got x and y, the variables from a Cartesian equation, but we've also got this extra parameter lambda involved. So both of these equations now, if we wanted to, we could rearrange them so that lambda was the subject of the equation. So this one would be x take 3 over 2. We could say that lambda was equal to x take 3 over 2. And for this equation, we could say that lambda was equal to adding 4 to both sides, y plus 4, and dividing both sides by 5, y plus 4 over 5. Okay, so still parametric equations. I've just expressed them now with lambda as the subject of the equation. So these would normally be considered to be our parametric equations here. Part C of the question then, we can work out the Cartesian equation of the line by equating these lambda values here. So we can actually say that x take 3 over 2, which is equal to lambda, is in fact equal to y plus 4 over 5, because that's also equal to lambda. I'll just run through that again. So this lambda x take 3 over 2 will be equal to this value of lambda, y plus 4 over 5. So we can equate those values of lambda. And then we can just tidy that up a little bit so we can get it in that isn't a Cartesian equation, but we like to perhaps tidy it up a little bit. So multiplying both sides by 5, we'll get 5x take 3 equals, multiplying both sides by 2, we'll get 2y plus 4. We can expand those out to get 5x take 15 equals 2y plus 8. And then perhaps we might make 2y the subject of our equation. So we've got 2y is equal to 5x, so we're subtracting 8 from both sides, so we get take 23. And that's probably good enough for our Cartesian equation if you wanted to. You could make y the subject of the equation, 5x take 23 over 2. So there's our Cartesian equation of this line here.